The last part of this lecture, we want to look at reactive oxygen species. When we look at the definition, reactive oxygen species, a lot of times just called ROS, is generated when oxygen is only partially reduced. And this shows here molecular oxygen in the different forms of reactive oxygen species that can occur as it is fully reduced to form water. So we can go through the superoxide radical. We have peroxide, hydrogen peroxide if two hydrogens are associated with it, and also the hydroxyl radical. Now, superoxide radical is the best known ROS, and it serves as a precursor by which other types of reactive oxygen species are generated. Hydroxyl radical is the most potent oxygen radical to exist. And the thing about the hydroxyl radical is it actually comes from peroxide, and it can react with iron, where we have essentially the splitting of the peroxide. And because iron can go from the 2+ to the 3+ state, we can donate, so we have hydroxide, but it leaves behind superoxide radical. And this stuff is incredibly damaging within a cell. It reacts with everything. And another issue to note is that single electron transfers happen as part of the electron transport chain. And you may not have known, but the mitochondrial matrix has high amounts of iron stored because of all the redox centers and the ETC complexes, enzymes that rely on this iron. So having hydrogen peroxide around as well as iron also makes possible this Fenton chemistry and thus production of hydroxyl radical. So when we look at Fenton chemistry, again, the way electrons are transferred, we start here with O2. We know that as part of the process, we generate hydrogen peroxide. Iron is naturally stored in the mitochondrial matrix. And so one of the observations is to look at iron levels and what is happening in terms of disease state. So we probably have all heard if you're deficient in iron, we call that anemia. It can be bad again if you don't have enough iron. All these proteins or enzymes that rely on these irons aren't going to be able to do what they're designed to do. But with iron overload and too much iron, this is what leads to the Fenton reaction or Fenton chemistry, which gives rise to that hydroxyl radical that is so damaging of biomolecules. Now, your body has a number of antioxidant mechanisms that can occur. We have naturally antioxidants that can bind associated with membranes that can be hopefully altruistic in their life goal, where these particular molecules can be damaged by free radicals before something important is damaged. And then you also have these different enzymes that are going to target ROS to get rid of them. So superoxide dismutase was discovered in 1969, and it's going to take superoxide anion and it's going to convert it to hydrogen peroxide. And then we have glutathione peroxidase and catalase, two different enzymes that are going to target hydrogen peroxide in order to convert it to water to hopefully prevent any of the hydroxyl radical from having much of a chance to form. So we're going to look at each of these enzymes. Superoxide dismutase is going to facilitate a reaction in which two superoxide radicals are going to be bound with two protons in order to produce hydrogen peroxide and molecular oxygen. Now, this particular enzyme is found in both the cytosol as well as the mitochondrial matrix. Typically in the mitochondrial matrix, the iron center is going to be manganese, whereas in the cytosol, they typically are going to have copper and zinc. Now, the form in the mitochondrial matrix deals with more endogenous ROS that's naturally made within the matrix of the mitochondria because of single electron transfers. But it's also important superoxide dismutase in the cytosol because you can also have exogenous ROS that can either come from the environment or leaking of ROS through a damaged mitochondria. So that's why this is found in both locations. Rates are near diffusion controlled limits as electrostatic guidance of these negatively charged superoxide is taken into the active site where these metal centers are found. So this enzyme is going to function, again, it's going to pick up this superoxide radical. And what it's going to do is to allow for it to react with the metal center. So we get an electron transferred to the metal. So it goes from this place copper 2+ to copper 1+. That's going to allow the release of molecular oxygen. And then by picking up two protons and a second superoxide radical, we can then reverse course, allow for electron its copper unit to be donated. So it goes back to the 2+ state. And then we have everything we need in terms of electrons for bonds to form between molecular oxygen and the hydrogens so that we can allow for peroxide to be formed. So these then become the two products of superoxide dismutase. And this is the first line of defense against reactive oxygen species. Of course, we have to be careful with hydrogen peroxide. We don't want it to be in too high of a level of Fenton chemistry to occur. So hydrogen peroxide gets converted, has to be converted to other more safe molecules. And that's why they're targeted by, why hydrogen peroxide is targeted by catalase and glutathione peroxidase to convert it to water. So the idea is that your body's defense is going to allow for catalase, glutathione peroxidase to act before any type of Fenton chemistry can occur. So if we look here, we've talked about superoxide dismutase and how it takes superoxide and converts it to molecular oxygen and hydrogen peroxide. Now we're going to look at the actions of catalase, and it takes hydrogen peroxide and converts it to water and molecular oxygen as well. And then glutathione peroxidase, that's going to take hydrogen peroxide and allow for its conversion to water. So when we look at glutathione, it has this reactive sulfhydryl group here, and this is going to be where chemistry is going to occur. So if we look at this reaction, glutathione peroxidase eliminates peroxides where it's in its reduced form, and it can serve to donate electrons to the peroxide. And that's going to allow for its conversion to water and whatever alcohol group that the rest of this may be contained to, and it goes now to its oxidized form. So it's changing its oxidation state. So this is the action of glutathione peroxidase. We also have to then have glutathione peroxidase in its oxidized form to go back to the reduced form, because this is what is the active form in terms of ROS protection. And so it turns out there's another enzyme called glutathione reductase, and it's going to play a role in getting glutathione peroxidase to its active role. Glutathione reductase relies on electrons from NADPH in order to allow for the redox reaction so that glutathione is regenerated in its reduced form, producing NAD+. So we know NADPH has been important as electron carrier for biosynthesis, but its levels also play an important role in allowing for ROS protection. So again, glutathione reductase is found in cell types to eliminate hydrogen peroxide. When we look at the action of glutathione peroxidase, we see that it goes from its reduced, and this is where it's active again for ROS, and I'm going to call that cleanup, to get rid of it, get rid of the hydrogen peroxide so Fenton chemistry can't occur. And then it goes into its oxidized state. Then we have the action of glutathione reductase, and it's going to be dependent upon NADPH as the electron source to regenerate the active form of glutathione. Again, this is found in mitochondria as a way to eliminate H2O2 or hydrogen peroxide. And remember that levels of iron can be high in the matrix, and hydrogen peroxide with levels of iron are what are going to allow for Fenton chemistry, and Fenton chemistry is what allows for the hydroxyl radical, which is deadly. So it's important that this enzyme be able to function and to target that hydrogen peroxide. The third one is catalase, and turns out the mechanism is not actually known for catalase, but it's believed to occur in two phases that are shown here that involve the use of a heme, whereby a radical is generated as part of the reaction mechanism. So it's going to require two hydrogen peroxides and the use of an iron that's going to have a change in oxidation state. And again, we're not going to go through the mechanism, but we can see these single electron transfers that allow for peroxides to be picked up and ultimately converted to water and molecular oxygen. Now, catalase is found in all living organisms that are exposed to oxygen, and it has one of the fastest turnover rates observed for enzymes. How important it is to get rid of this hydrogen peroxide so that hydroxyl radical doesn't have a chance in forming. As a matter of fact, in terms of KCAT, it has a reaction. What is that number? Think about it. 10 million molecules of hydrogen peroxide can be converted to water and molecular oxygen per second. So almost approaching those diffusion controlled limits. As quick as enzyme and substrate come into contact, product is already being produced. Now, when we look at catalase, it's also important in looking at its activity and shielding cells from oxidative injury. So there's two things that they've looked at, hydrogen peroxide and antimyosin A. And the mitochondria catalase is shown to protect from those. But we can take it even a step further, that when we look at catalase becoming more and more active, we also see an increased sensitivity to the cells to the tumor necrosis factor, the alpha-induced factor. Why does that matter? Because that's going to trigger apoptosis. So what this statement is saying is the more you see catalase being used in cells, the more sensitive the cells become to apoptosis. And that is actually a great thing, because if too much hydrogen peroxide is constantly being generated and the cell is having to respond to it, then something's probably going wrong in that cell. And so it can trigger apoptosis or cell death as a way of protecting other cells from the same type damage. And so that's been a unique study now that's been looked at for a few decades, where we can tell, how well the cell is maintaining things. And I just wanted to bring up, it says and antimyosin A. So we know hydrogen peroxide, and we can correlate that to ROS. What is antimyosin A? Well, it's actually an antibiotic substance that's produced by Streptomyces species that inhibits mitochondrial respiration. So cells can also be infected, and this can also cause that alteration and protecting the cell, other cells through apoptosis. So why do we care about oxidative stress at all? Well, remember that you have endogenous ROS. This is going to be generated as part of normal metabolism of oxygen. We've talked about single electron transfers that happen as part of the electron transport chain that's going to be occurring in mitochondrial matrix of all mitochondria and all cells. So that's going to be natural just to how our body uses this system to generate energy. You also have exogenous ROS, things that are generated from different pollutants, tobacco use, smoking, drugs, radiation exposure. So oxidative stress is a huge signaling point for the cell to have to take care of. And in all different cell types, when we look at what oxidative stress can cause, and that's what this figure does. I don't want you to memorize it, but just instead look at what types of things happen. So, start with the brain. If we look here at the brain, trauma, stroke, neurotoxins, Parkinson's, Alzheimer's diseases have been linked to mismanagement of long-term oxidative stress that can manifest. Lungs, asthma, ARDS, hyperoxia, joints, rheumatoid arthritis. And then I just wanted to point it here, multi-organ radiation, you have aging, cancer, inflammatory, immune, you can have different injuries, how blood flow is done, diabetes. So across the board, we care about oxidative stress because of the number of different disease states that it leads to. So understanding how your body protects naturally against endogenous ROS is important, and minimizing your exposure to exogenous ROS as best as possible also becomes important. A number of degenerative diseases are associated with oxidative damages to the mitochondria, and this has actually led to what is called free radical theory of aging. Why are lifespans typically what they are? You have medicine, you have better eating, sleeping, health habits. But again, there's just certain periods of time that people typically are living through. And what they're finding is a correlation to the amount of free radical reactions that occur just during a normal course of oxidative metabolism is at least partially responsible for not only aging process, but also what type of life duration typically is experienced.